What specific problem does deep cross-attention aim to address within the context of residual networks? And how does this relate to the concept of information dilution?
Deep cross-attention, DCA, aims to address the problem of information dilution in residual networks, which arises from the equal treatment of all previous layer outputs when they are summed in the residual connections. This dilution can lead to the loss of useful information from select layers, as the model may not effectively prioritize the most relevant information. DCA resolves this issue by employing learnable, input-dependent weights that allow each layer to dynamically combine outputs from previous layers, enabling the model to selectively focus on the most pertinent information. This approach enhances the model's capacity to recover the input and improves overall performance, as evidenced by DCA's superior results compared to traditional residual networks. By mitigating information dilution, DCA enhances the effectiveness of the residual learning framework in transformer architectures.
How does the proposed deep cross-attention method work? Illustrate the methodology step by step, including the role of GRNv3 and the overall architecture within a transformer block.
The proposed deep cross-attention DCA method enhances the transformer architecture by integrating three independent instances of a generalized residual network, GRNv3, within each decoder block. First, DCA takes the stack of outputs from previous layers as input to these GRN instances, which are responsible for generating the queries, keys, and values for the attention mechanism. The GRNv3 allows for input-dependent weights, enabling the model to dynamically adjust the importance of different layer outputs based on the current input, thus preventing information dilution. This architecture facilitates richer interactions between layers at varying depths without altering the underlying attention mechanism. Overall, DCA effectively combines the outputs of earlier residual blocks, allowing for a more flexible and efficient representation of information, which leads to improved performance in language modeling tasks.
Can you provide a simple example illustrating how the input-dependent weights in GRNv3 function within the DCA architecture? Walk through the steps of how a sample input is processed through the network.
In the deep cross-attention DCA architecture, the input-dependent weights in GRNv3 function by dynamically adjusting the contribution of previous layer outputs based on the current input. For a sample input, X, the process begins by passing X through the initial layers of the transformer, generating outputs that are collected into a stack, G_T. In GRNv3, the weights, B_T, are initialized as all zeros and optimized during training, while an additional component, bar W_T, is derived from a nonlinear mapping of the input, X. When the output of the TTH layer is computed, it is expressed as G_Tx equals G_T CDOT B_T, CDOT1, where B_T is influenced by both the learned weights and the input-dependent component, bar W_T. This allows the model to selectively emphasize certain features of the input based on its characteristics, effectively rearranging the contributions of previous layers. As a result, the final output of the DCA architecture is a refined representation that leverages the most relevant information from the earlier layers, thus preventing information dilution and enhancing model performance.
What are the practical advantages of using DCA compared to standard transformer architectures in terms of performance metrics such as perplexity and training efficiency?
The practical advantages of using deep cross-attention, DCA, compared to standard transformer architectures include significantly lower perplexity and improved training efficiency. In experiments, DCA consistently outperformed standard transformers on language modeling tasks, achieving lower perplexity for a given parameter budget and training time. For instance, the 30-layer DCA model achieved better perplexity than a 42-layer transformer, demonstrating its parameter efficiency. Additionally, DCA exhibited enhanced training stability, mitigating the occurrence of loss spikes that are often problematic in large model training. Overall, DCA's design allows for richer interactions between layers and more effective information utilization, leading to superior performance metrics.
How was the effectiveness of deep cross-attention validated in the experiments? Describe the datasets used, experimental design, and the metrics employed for performance evaluation.
The effectiveness of deep cross-attention, DCA, was validated through experiments on language modeling tasks using the LM1B and C4 datasets. In the experimental design, models were pre-trained with an embedding dimension of 512 and an MLP dimension 4 times larger, trained over 500K steps totaling 131 billion tokens. The performance evaluation metrics focused on perplexity, where DCA consistently achieved lower perplexity for a given parameter budget compared to standard transformer architectures, demonstrating improved training efficiency. Additionally, the experiments included variations in model depth and width, showing that DCA maintained its advantages even as model complexity increased. The results indicated that DCA not only outperformed standard transformers, but also exhibited improved training stability, mitigating loss spikes commonly observed in large models.
What specific results were obtained when comparing DCA to standard transformer architectures, and what do these results suggest about the performance improvements that DCA provides?
When comparing deep cross-attention, DCA, to standard transformer architectures, the results demonstrated that DCA consistently achieved lower perplexity for a given parameter budget and training time, indicating enhanced efficiency. Specifically, in experiments on language modeling tasks, DCA outperformed the standard transformer by obtaining better perplexity, even with fewer training examples, achieving extremely small loss values. Additionally, DCA exhibited improved training stability, mitigating the occurrence of loss spikes that are frequently observed in large model training. The results also showed that DCA's performance improved as model depth increased, with a 30-layer DCA model outperforming a 42-layer standard transformer, highlighting its parameter efficiency. Overall, these findings suggest that DCA significantly enhances model capacity and training efficiency compared to traditional transformer architectures.